Welcome back to part 2 on an overview of non-local wealth inequality dynamics and capitalism. In this one, we're going to be covering economic drift, economic diffusion, Pareto tells, economic cohomology, von Neumann entropy, and Lindbladians. We'll bring back our derived Fokker-Planck equation for the time evolution of wealth concentration from our last video. This is to say, the time evolution of our wealth distribution is equal to minus the partial derivative in respect to omega of our drift of our wealth distribution plus the second derivative in respect to omega of our diffusion of our wealth distribution. We now wish to consider a stationary distribution as a time-independent solution with zero probability flux at infinity. Stationarity here refers to vanishing probability flux at infinity, and that does not imply a static nor closed economy. It just enforces finite wealth accumulation in finite time. For this to maintain zero probability flux at infinity, our stationary distribution must satisfy the following. So the time derivative of rho sub infinity is equal to 0. Plugging this into the Fokker-Planck equation yields the following. The drift term, A of omega, is linear in wealth and can be used to measure proportional growth, such as capital accumulation, where alpha denotes a drift coefficient. When the drift coefficient is greater than 0, we have a positive drift of wealth, and this is a measurement of capital's advantage. This disproportionately benefits those who already have accumulated lots of wealth at the cost of reducing availability to the majority. Any solution surrounding the creation of new money increases inflation, so value is then reduced. The diffusion term d of omega is a quadratic term that can be used to measure multiplicative volatility, where sigma denotes a diffusion coefficient. When the diffusion coefficient is greater than 0, this denotes the volatility of wealth transfers. Combined, these terms encode the observation that those holding capital power tend to experience larger absolute fluctuations. In words, the rich get richer while the non-rich get progressively poorer in return. It is within this revelation that we can discover a Pareto power law, also known as the 80-20 rule. Let's see if we can make this explicit. First, we plug our terms into the stationary Fokker-Planck equation. An interesting point to make as an aside is that this is essentially a forward/adjoint time-independent form of the Black-Scholes equation, which, under time dependence, governs price evolution of contracts between buyers and sellers when wealth is replaced by an underlying price S and alpha is replaced with the risk-free rate R. Regardless, let's get back to the topic at hand. Keep in mind that the stationarity here is not a claim about human behavior being static or in equilibrium. What we are dealing with here is a statement about an invariant measure induced by structural mechanisms. The statement of the partial derivative of our wealth distribution being 0 does not mean that agents stop interacting, adapting, or behaving dynamically. All this says is that the distribution is invariant under the dynamics created by the drift and diffusion operators. While trades occur, firms are created or destroyed, workers move, wages change, policies shift, and shocks occur microscopically, the shape of the wealth distribution itself remains stable up to normalization and scale. Most human systems do not admit stationary distributions because interactions are bounded, conservation laws are weak or absent, and feedback loops saturate the dynamics. Capitalist wealth accumulation is different for one decisive reason, and that reason is because capital accumulation acts as a multiplicative growth channel by design. As long as private property persists, losses are at least partially socialized, and gains are privately accumulated, the drift operator remains positive and multiplicative. Complexity lives in the fluctuations, whereas power resides in the invariant measure itself. Positive drift is a structural asymmetry as opposed to a rational choice. The solution we shall discover to the Fokker-Planck equation here will reveal what persists despite endogenous complexity. Now we begin solving for rho sub infinity. When we integrate once across the equation, we obtain the following. We lack a constant on the right-hand side because of our flux condition, so we don't see the constant of integration. Now we rearrange to obtain the following. We perform the derivative on the right-hand side using the power rule and the product rule to obtain the following. Now we divide through by the wealth omega. Rearranging and organizing, we obtain 1/2 sigma squared times omega of the derivative of the wealth distribution at infinity equals the constant alpha minus sigma squared times our wealth distribution. Now we multiply through by 2 to get rid of that fraction. Now we divide through by sigma squared. Divide through, again, by the wealth. We isolate the derivative of our wealth distribution. And now we divide through by the wealth distribution to isolate distribution terms. We now have an equation that allows us to easily solve for the stationary wealth distribution by integrating both sides. We normally obtain natural logarithms of absolute values when performing these integrals, but since we are working with the case where densities in wealth are greater than or equal to 0, as we discovered in our last video, we don't need absolute values here since our results will be positive anyway. This leaves us with the following. We have the natural log of rho sub infinity equals 2 times alpha minus sigma squared divided by sigma squared times the natural log of wealth plus our constant of integration. Exponentiating both sides yields our solution for rho sub infinity. To make the behavior of the exponent clearer for economic purposes, we can write it to obtain that rho sub infinity equals a constant times omega to the power of negative 2 times 1 minus alpha divided by sigma squared. Rho sub infinity has a Pareto form omega to the power of negative k, and it is indeed integrable ad infinity, hence admissible as a stationary tell when alpha divided by sigma squared is less than 1/2. We have discovered that, under capitalist wealth accumulation, a Pareto power law is a stationary solution of the Fokker-Planck equation. As such, wealth inequality cannot be avoided under capitalism so long as one desires to keep capitalism stable. The system stabilizes to a heavy-tailed wealth distribution, of which the 80-20 rule is a common empirical instance. In a capitalist system, liberal economic reform tends to target the diffusion coefficient, sigma squared, in order to balance out the positive value of the drift coefficient, alpha. Now let's look back at our stationary Fokker-Planck equation to make more sense of this. Our drift term is, effectively, the simplest object to concern ourselves with for this analysis. A capitalist wealth distribution must, at very minimum, rely on a positive and growing drift coefficient, or else the principles of capitalist wealth accumulation no longer hold, and thus the system fails to be a growing and successful capitalist system. Our entire drift term is under the action of a first-order derivative, so gauging how this drift evolves in respect to wealth is rather simple. It governs the flow of wealth through an economic phase space. On the other hand, the diffusion term is under the effect of a second-order derivative, and if you're familiar with calculus, you know that the second-order derivative effectively measures the curvature of a function. This equation, then, tells us that as wealth deterministically evolves through an economic phase space via drift, it undergoes curvature through the same phase space via diffusion, which brings in non-deterministic behavior. This implies that what happens to the economic system through drift is non-linearly perturbed by what happens through diffusion. This diffusion is what measures the tendency of wealth to spread, mix, or concentrate in response to policy, agent preferences, and more. To reiterate, liberal economic policy corresponds mathematically to adjusting the diffusion coefficient, whereas capitalist accumulation corresponds to increasing the drift coefficient. The ratio between these things determines the heavy tail exponent of wealth inequality. This means that no matter what liberal reform does to target wealth diffusion, capitalism can make up for it by increasing drift in order to perpetually increase profit at the cost of the majority. There is no policy lever, no ethical reform, and no quote-unquote good capitalism that changes this fact unless you drive alpha to zero or make sigma squared diverge to infinity, and there is no such finite implementation of policy capable of causing infinite diffusion, and if such a thing did exist, the system would no longer be capitalist by design. Therefore, while liberal wealth reform can temporarily stabilize the experience many people have locally under capitalism, it simply cannot abolish structural inequality. We may think of the wealth field we expressed as a section of a line bundle over a base space of agents and time. Gauge theory then provides a powerful language for local units and rescaling of wealth. In this regime, a gauge transformation is a local rescaling of the wealth distribution field by a factor e to the power of lambda of omega and t. This represents a local change of units, price level, or currency normalization. A physically meaningful description of accumulation must be invariant under such local reparameterizations, that is to say, the choice of units should not change who is rich or poor. We may also introduce a gauge potential, a sub mu, called a connection, where temporal and wealth space components encode local accumulation and redistribution rates. The drift coefficient alpha can be viewed as the component of a connection along the wealth direction, which we model through the following gauge covariant derivatives. So the covariant derivative for rho in the direction of time is equal to the partial time derivative of wealth distribution plus the connection over time of wealth distribution. The same then applies for omega. The continuity equation is the gauge theoretic statement of local wealth conservation. Where J here is equal to A of omega times rho minus the partial derivative in respect to omega of D of omega times rho. This states that change in local wealth density equals net flux through that point. In more general models, the connection hosts non-trivial curvature is given by the following curvature form, where D is the exterior derivative from the d-Rom complex, A is the connection 1 form, and the wedge denotes the exterior product. Non-zero curvature means that accumulated wealth after moving through the economic network depends on the path taken. This is to say that it matters who trades with who, in what order that trade occurs, and under what local policies trade is conducted under. This mirrors the structure of electromagnetism and gravity, but instead of electromagnetic and gravitational fields being the curvature of a connection, we have fields of exploitation and redistribution being the curvature on a wealth bundle. Thus, gauge theory encodes local conservation, local accumulation, and the geometric obstruction, or otherwise the curvature, that makes accumulation path-dependent. The drift and diffusion coefficients are then the gauge covariant data seen in the Fokker-Planck equation from earlier. Category theory, as we shall utilize it, then steps back and organizes entire economic regimes and their transitions. We can define a category of economies, denoted econ, whose objects X are parameter sets or data sets of a macro regime, where alpha denotes the drift, D denotes the diffusion, gamma denotes boundary structure, and G denotes gauge structure. We can also have other structures here as needed. A morphism F that maps us from X to Y in the category of economies is a policy or structural transformation changing the data where tax reforms, nationalizations, and decommodification correspond to changes in drift and diffusion. The opening and closing of markets correspond to changes in gamma and G, the boundary structure and gauge structure, respectively. Formally, the morphism F induces a map on parameters. So F takes us from any, let's say, letter A sub X to a letter A sub Y. A functor Fp takes us from the category of economies and maps us to the category of generators, which we denote by gen. This functor sends each regime X to its Fokker-Planck generator L sub X, which is a differential operator, and sends each morphism F that maps us from X to Y to the intertwiner between generators. Another functor, which will denote stat, takes us from the category of economies and maps us to the category of distributions, which we shall denote dist. This functor sends each regime X to its stationary distribution when it exists. Natural transformations between functors encode renormalization or course grading of the economic system, expressing how macro statistics emerge from micro rules. Altogether, we can use category theory to organize the space of economic systems as a category, the policies as morphisms, and the Fokker-Planck generator or stationary distributions as functorial constructions. We can use operator algebras to provide the analytic framework for time evolution of the wealth distribution and observables. Let L be the Fokker-Planck operator. It takes the same form as our regular Fokker-Planck equation. I'm just writing it out in operator form explicitly. On a suitable function space, L generates a Markov semigroup. E to the power of t times L, where rho sub t is equal to t sub t of rho naught. Now consider a C-star algebra A of bounded observables, functions f of omega acting by multiplication. A state on A is a positive normalized linear functional. In a commutative case, each density field rho of omega in T defines the following state. That is the definite integral from 0 to infinity of f of omega, rho of omega in T, and this is integrated in respect to omega. Time evolution can then be stated in terms of the Schrödinger picture that maps us from rho naught to rho sub t, or in terms of the Heisenberg picture through the dual sigma group alpha sub t of f equals f sub t, with the generator L dagger. The stationary distribution rho sub infinity corresponds to an eigenstate of L with an eigenvalue of 0, or a KMS-like equilibrium state for the semigroup. The spectral gap of L controls the rate at which any initial wealth distribution relaxes to the Pareto tell, and this can provide a more rigorous expression of the idea that inequality is an attractor. In a non-commutative generalization, such as with multiple coupled markets, we work with non-commutative operator algebras, such as von Neumann algebras, quantum Markov semigroups, etc. We will spend time considering a non-commutative case later. We fix the macro regime X that we defined earlier for the following discussion. Let R be a commutative ring. We can think of it in terms of the real numbers or of the space of bounded measurable functions on a wealth space denoted L infinity of capital omega. We can now define three R modules for the regime X. 1, M sub X, which is the module of labor inputs, such as, say, labor hours. W sub X, which is the module of wage payments to workers. V sub X, which is the module of value created, given in money units at current prices. We then have canonical R linear maps. L sub X maps us from the module labor inputs into the module of value created. Omega sub X maps us from the module of labor inputs into the module of wage payments. And pi sub X maps us from the module of value created into the module of wage payments. L sub X corresponds to the realization of labor's value, omega sub X corresponds to the assignment of wages to labor, and pi sub X corresponds to the part of value that is actually paid as wages. In an ideal non-exploitative world, we would demand that the following diagram is exact. Under this diagram, we note that the kernel of pi sub X equals the image of L sub X, and the kernel of L sub X is trivial, therefore equal to 0. Under the capitalist constraints we have experienced, the diagram above is not exact. Nonetheless, with this information, we can define a chain complex. We can refer to different sectors of this chain complex with the following instances of the chain complex itself. So C sub 2 of x is equal to 0. Moving over once gives us C sub 1 of x, which is, of course, the module of labor inputs. Shifting over once more, C sub 0 of x gives us the module of value created. C sub negative 1 of x gives us the module of wage payments to workers, and then we go back to 0 with C sub negative 2. We also have a composition of differential operators within the chain complex. So D naught composed with D sub 1 is equal to pi sub x composed with L sub x. And in an exact regime, we would have the following, where that composition we just mentioned is equal to omega sub x. Since we are in a non-exact regime, the composition above measures the failure of exactness. And this is where exploitation hides itself within capitalist economies, and shows that exploitation does not have to be made obvious for the results of exploitation to be made real and experiential. Our homology is then defined by the following. We have the kernel of d sub I modulo the image of d sub I plus 1. We now denote two important values of this homology. H sub 1 of x gives us the kernel of L sub x, and H sub 0 of x, or H naught of x if you will, gives us the kernel of pi sub x modulo the image of L sub x. H sub 1 of x corresponds with labor inputs that are not realized as value, and this can be demonstrated by wasted or underutilized labor and unemployment. H naught of x corresponds with value that is not captured as wages and is not directly equal to realized labor. This is a cohomology class of surplus value. So the contemporary concern of exploitation through surplus value can then be recognized as the failure of this homology to vanish at degree 0. If the secrets were exact at v sub x, then every unit of value would either be fully explained by wages or be outright impossible. Exploitation is profitable due to the non-exactness of this sequence, as a non-vanishing homology at degree 0 yields excess value beyond wages. Importantly, this is all orthogonal to operating costs such as rent, electricity bills, depreciation, maintenance, logistics, etc. So that has nothing to do with the exploitation here. We now move from a single regime to an abelian category A of labor configurations, where our objects M, V, and W form a triple. We have the same structure maps L and pi from before, and morphisms are commuting diagrams between such triples. We can define a left exact functor that, quote-unquote, forgets everything except realized wages. And that's what this curly W will do to our triple. This is an example of a forgetful functor. Because our forgetful functor is left exact, its right-derived functors measure the failure of exactness of wages with respect to the underlying labor value configuration, and as such, this collection of right-derived functors acting on our triple is isomorphic to the homology class at degree 0. This allows us to formally define a profit extraction functor as a derived functor. On each regime X, this derived functor is the cohomological leftover between total value and wages, e.g., profit from exploitation. We can then consider the rate of exploitation as the dimension of the cohomology group. We choose a base field K to be the set of real numbers, and we thus view modules as finite dimensional real vector spaces for our case. The rate of exploitation for a regime X is the rank of the cohomology group normalized by total labor capacity. The measure of exploitation rate in H naught of x, which we shall denote as an invariant E of x, is then given as the following. The kth dimension of H naught of x. It can then be argued reasonably that exploitation vanishes if and only if the dimension of our homology group at degree 0 is itself equal to 0, and thus E of x is equal to 0. We can take more or less this exact same information and reframe this within the language of sheaf theory to see what else we can uncover once the dust settles. Let S be a topological space of sectors. For each U that is an open subset of the topological space of sectors, we define three fundamental objects. M of U is labor inputs in the sector U. V of U is the value created in the sector. W of U are the wages paid in the sector. Assuming restriction maps are compatible with the structure maps, the following complex is a pre-sheaf of chain complexes. Where again we have L and pi as before, upgraded into the information for a sheaf theory. Sheafification of each level gives a sheaf complex C plus with sheaves M, V, and W. For each degree I, we can consider cohomology sheaves. That is the kernel of d sub I modulo the image of d sub I plus 1. H0 is the sheaf of local surplus value classes, and H sub 1 is the sheaf of unused or blocked labor. With this information in mind, we consider the global section functor, which effectively sends a sheaf to its global observables. Applying this global section functor to a sheaf of vector spaces, modules, or chain complexes yields a global complex of modules. In an economic sense, passing from pre-sheaf chain complexes to global sections behaves like taking global labor allocations across the economic base space. This allows us to think of global complexes. Even if locally in each U the sequence is exact, implying no local exploitation, we may still have a non-zero global cohomology. This means that exploitative relations become cohomological obstructions to descent, meaning local fairness induced on overlaps of open subsets of the topological space cannot be glued consistently into a globally non-exploitative wage value structure on the entirety of that topological space. If our study of labor exploitation is restricted to a single nation, then that means the failure of exactness globally implies that reforms enacted on states do not coherently merge to produce effective reform at a federal level, and reforms enacted on municipalities, or cities if you will, do not coherently merge to produce effective reform on a state level. If we treat capitalist imperialism on a planetary scale, a non-vanishing HI indicates that even if, somehow, every capitalist nation achieves fairness internally, the global gluing problem forces inequity to appear on the boundary of that system. So fairness in one region mathematically induces unfairness to those outside the region, because the drift term defining wealth accumulation is fundamentally a global structure. This demonstrates that exploitation is not merely a contingent byproduct of capitalism, but rather a structural feature of the value form that capitalism relies upon to exist in the first place. Thus, even if the entire world becomes a unified capitalist regime, the drift inherent to capital accumulation mathematically forces exploitation to expand beyond the original domain of coherence. If the only remaining exterior region is extraplanetary, exploitation will expand there. Therefore, imperialism is not simply a historical tendency of capitalism, but rather a mathematically necessary cohomological consequence of private wealth accumulation itself. The obstruction class has no natural bounds, and imperial expansion is the process of attempting, and failing, to kill a non-zero cohomology class by enlarging the indexing category. So the system must create new open sets, because the obstruction will not vanish under endomorphisms internal to the given sheaf. Exploitation is the image of the capitalist value form under the connecting homomorphism of a long exact sequence in cohomology, and therefore cannot be terminated by local reforms at any scale. Capitalist exploitation cannot be solved by reform because reform leaves the chain complex unchanged. For liberation to occur, complete abolition must be the driving force. To state this more simply, capitalist exploitation cannot be resolved by local reform, but rather by its evaporation as a form altogether and through its replacement by another form entirely. Going back to a purely economic framing and considering another scenario, let's suppose that we have an intended fair wage pre-sheaf that assigns to each sector U of our topological space a notional fair wage distribution, but let's say it fails to be a sheaf because each sector has different bargaining power or legal regimes, thus causing gluing conditions to fail. The sheafification of our pre-sheaf computes the closest genuine sheaf approximating the intended fair wage assignments. It enforces global compatibility by gluing consistent local wage data across overlapping sectors. Since this does not equate to an actual observed wage sheaf, we end up with the following discrepancy that we'll call D. This is a sheaf that captures wage distortion, and it features a cohomology in terms of H0 of S and D, H1 of S and D, etc. This cohomology, under which singular, DROM, and sheaf cohomologies are special cases, being non-trivial, signifies structural wage heterogeneity that cannot be eliminated by local reform. And the reason for this failure of elimination is precisely because the obstruction lives in the higher cohomology of the sheaf itself. Wage inequalities correspond to failures of exactness in the global section functor applied to the distortion sheaf, whereas liberal reform corresponds to local reform that changes sections on small open sets in this case, and thus cannot touch the global section. In the prior scenario, we saw that cohomology measures a failure of descent in an existing sheaf, in this case resembling a structural impossibility within capitalism itself. In this scenario, cohomology measures a failure of sheafification of a prescriptive fairness pre-sheaf. In either scenario, we find that the exploitation inherent to capitalism cannot be resolved through reforms that are internal to capitalism. To put it into other words, in the descent obstruction scenario, the non-vanishing cohomology indicates that exploitation is a global obstruction to exactness within the existing value form complex. Local reforms correspond to co-boundary adjustments, but no co-boundary can kill a non-trivial cohomology class. In the distortion sheaf scenario that we just discovered, the failure of the pre-sheaf to be a sheaf and the persistence of non-zero cohomology in the distortion sheaf demonstrates that any attempt to impose fairness as a reform internal to the existing wage system will always produce residual distortion. So we find through these scenarios that reform is a co-boundary operation, while exploitation is an entire cohomology class. A co-boundary cannot annihilate a cohomology class inside the same complex. Therefore, internal reforms cannot erase exploitation. We find that liberation is achieved by removing the obstruction class altogether, and this requires replacing the underlying structural complex of capitalism. Let A sub x be the abelian category of sheaves of labor, value, and wage modules over the sector space S sub x of regime X. Its derived category, D plus of A sub x, packages all chain complexes up to quasi-isomorphism. We now consider a scale coarsening map, where pi sub A maps us from the micro sector space to the macro sector space of regime X. This induces a pullback functor and push-forward functor, respectively. So pi upper star sub lambda takes us from macro to micro, and pi sub lambda star takes us from micro to macro. And in this case, these are abelian categories. Because pi sub lambda star is left exact, its right derived functors record how micro-level exploitation survives at macro scales. The following induced functor on derived categories is a renormalization group step. The renormalization group itself is then a family of these functors, graded by real numbers that are greater than or equal to 0, whose composition corresponds to addition of scale parameters. Renormalization group flows then describe how micro-labor exploitation scales to macro inequality via the flow of cohomology groups under the derived functor. Fixed points of this flow correspond to macro regimes where inequality becomes scale invariant, inevitably yielding a stable Pareto tell. Earlier, we already established a 1 category denoted econ with regimes X, and morphisms F that map us from X to Y. Now we define a 2 category that we shall denote econ 2, where 0 cells are the regimes X of the 1 category econ, 1 cells are the 1 morphisms F that map us from X to Y that we defined for econ, and 2 cells are 2 morphisms eta that map us from F to G that act as higher morphisms mapping us across 1 morphisms. These higher morphisms are natural transformations in the 2 category of economies. Our two-morphism eta is invertible when we can roll back a policy implementation into another without loss. When invertibility holds for these two morphisms, econ 2 is an example of a 2-1 category called a 2-groupoid. However, due to the nature of debt crises, austerity measures, capital flight, and privatization under crises we observe in practice, such two morphisms are not invertible within a capitalist regime, and thus econ 2 fails to be a groupoid in that case and becomes a 2-0 category. These irreversible structural adjustments are exactly the higher order abstraction classes we were working with in the sheaf framework that we saw earlier. This becomes really fascinating when we consider three categories, as consequences resulting from the entropy generated by failures of irreversibility in the two-category econ 2 correspond to the systematic crisis response to contradictions found within an economic regime. Since the two-morphism eta is itself a morphism, there can be different ways of modifying eta. In the 3 category that we shall denote econ 3, we retain economic regimes for 0 cells, regime transitions as 1 cells, and structural adjustments as 2 cells, just as before, but we now have 3 cells corresponding to transformations of transformations. 3 morphisms in econ 3 with a capitalist regime correspond to international finance negotiations over structural adjustments, World Bank renegotiations of International Monetary Fund conditionalities, judicial rulings modifying economic treaties, political coups reversing or partially redirecting austerity paths, and, especially in modern times, World Trade Organization trade dispute decisions altering the implementation of neoliberal reforms. Just as 2 cells are not invertible in a capitalist regime, 3 cells are even more path-dependent and historically irreversible. In effect, the International Monetary Fund imposes a structural adjustment plan, a national government negotiates portions, civil unrest forces partial rollback, and courts respond by ruling certain measures illegal. Under capitalism, social hierarchies are further weaponized as tools of this crisis response. But due to these conditions, we find that capitalist countries under crises tend toward an ultranationalist state characterized by hyper-privatization and hyper-individualism. This ultranationalist crisis response is referred to historically as fascism. Under fascism, it is abolitionism that becomes the obstruction theory, so capitalist countries tend to double down on enforcing policies that disproportionately harm abolitionist movements well before later stages of fascism are ultimately realized. However, recall that capitalism is the obstruction theory at the 2-category level, which makes it impossible for liberal reform to abolish capitalism and prevent fascism. Since abolition is the transitional obstruction theory at the 3-category level, we find that no local action under fascism can fully evaporate revolutionary tendency. Revolutionary tendency is then indicated by a new drift term in a higher categorical Fokker-Planck dynamic, where we find fascism to become promoted as a counter-revolutionary regime targeting diffusion. As a result, we see that fascism fails to abolish abolitionism for much the same reason liberalism fails to abolish capitalism and fascism. While we do not show the in-depth mathematical detail here, what we just discovered can be expressed using a Postnikov tower of economic regimes. Fascism equates to the preservation of a non-trivial Postnikov invariant. Abolitionist revolution then corresponds to forcing that invariant to vanish, and since the rise towards fascism is baked in capitalist contradiction, anti-fascist revolution must also evaporate capitalism to be effective. If not, the same 2-categorical collection of capitalist contradictions will give rise to another 3-category of crisis response. Four cells in a 4-category that we shall denote econ 4 relate whole histories of structural adjustments and resistance across different countries and epochs. This corresponds to shifts in global hegemony, creation and or dissolution of international bloc, such as the European Union, Lenin's Comintern, the BRICS, etc., as well as long-range reconfiguration of how coups, sanctions, debt regimes, and trade rules fit together globally. An example of an obstruction theory at this level could correspond to the issue of figuring out how to protect cultural self-determination of different peoples as we attempt to glue together different abolitionist experiments that arise across the world. Can a network of abolitionist movements across time and space be coherently glued into a stable global order that no longer reproduces the earlier obstruction classes? We do not yet know this answer. If the four-level obstructions vanish, we have the analog of a Postnikov tower where the higher invariants finally trivialize, and this means all higher cohomology of the distortion complex collapses. Thus, exploitation is not only locally and nationally abolished in that case, but globally and structurally stabilized under that ideal condition. Time will tell if struggle within the regime of these higher categorical theories will produce such outcomes. A 5-category, Econ 5, introduces 5 cells corresponding to transformations between world system coordination principles, capturing ecological, demographic, cultural, informational, and metabolic constraints on historical systems. The resulting 5-level obstruction theory expresses whether a world system is capable of sustainable global reproduction. Ultimately, at the infinity 1 categorical limit, stabilized abolition becomes the homotopic co-limit, a limit object of Postnikov filtration, of a Postnikov tower where all Postnikov invariants vanish. This corresponds to an abolitionist system that is obstruction-free at universal scale, and this would indicate a true post-scarcity economy. Thus, historical contradictions become universally exact, and classless reproduction can flourish without the hierarchies of racialization, gender discrimination, and more. Our next discussion will take us into the study of non-commutative geometry and von Neumann entropy, as we will treat financial networks as von Neumann algebras, also called W-star algebras, in order to discuss economic entropy more formally in terms of finance capitalism. Take a countable set of agents or accounts. Let H equal to the Banach-Hilbert space of accounts be a Hilbert space of this countable set. We now consider a von Neumann algebra M to be the space of bounded linear operators on the Hilbert space. More specifically, we allow this von Neumann algebra to be generated by a family of transfer operators that we shall denote as the collection of T sub ij. This family of transfer operators represents flows of capital from agent J to agent I. Each T sub ij can be a partial isometry sending E sub j toward E sub I. Projections P sub I that are elements of our von Neumann algebra onto subspaces spanned by groups of agents encode credit constraints, which shows who can receive or extend credit, as well as regulatory walls and segmentation between financial layers. Let the collection of U sub t, where t is greater than or equal to 0, be a strongly continuous one-parameter semigroup of contractions on the Hilbert space H that encodes time evolution of capital positions. Within this setup, non-commutativity appears because different sequences of trades generally do not commute. So T sub ij and T sub kl does not equal to the product of T sub kl and T sub ij. As a result, commodity circulation in finance capitalism becomes a non-commuting family of transfer operators that are subsets of the von Neumann algebra. This generates a dynamic non-commutative geometry. A state on our von Neumann algebra is a positive normalized linear functional phi that maps us from the von Neumann algebra into the complex numbers. For each time t, we have a state, phi sub t, and it evolves via the following. For normal states given by density matrices rho sub t on our Hilbert space, we can see the following evolution, where tr denotes the Hilbert trace and rho sub t is the wealth distribution over agents. We can now define a von Neumann entropy of our linear functional. That is minus the trace of rho sub t times the natural log of rho sub t. Growth of certain relative entropies, such as entropies relative to a fair reference state, encodes inequality. This means that inequality corresponds to entropy growth of states on these algebras. A persistent drift of entropy toward peaked spectra mirrors wealth concentration in a few eigenvectors, meaning wealth is concentrated into the hands of few at the net cost of many. This is the result of time asymmetry within capitalism, and thus saying inequality tends to emerge within capitalism is equivalent to saying the arrow of time tends to move forward. Both are statements of monotonic entropy increase under a non-invertible dynamical semigroup once coarse graining is applied. This is essentially isomorphic to the second law of thermodynamics. In effect, capital accumulation is a thermodynamic arrow of time in the economic algebra. Capitalism is therefore modeled as a completely positive but non-invertible map, an economic analog of open quantum systems with dissipation. Once again, we see that exploitation and wealth inequality are not anomalies in capitalism, but rather structurally encoded within its very fabric. This also implies that, given finite resources and laborers, increasing entropy pushes the system towards a heat death. And this heat death is reached exponentially faster if the bounds of exploitation are not constantly expanded. This is another reason why capitalism inevitably trends towards global imperialism. Consequently, liberal reform within capitalism is also funded not just by those paying taxes and those having their labor exploited within the system, but also by exploitation of communities outside of that system. We see this today through the exploitation of the Global South. The quantum Markov semigroup on the aforementioned states rho sub t is generated by a Lindbladian that we'll call L. And that is generated by the partial time derivative of our density matrix of wealth distribution. The Lindbladian takes the following GKSL form and generalizes the Schrödinger equation for open systems, where H is a self-adjoint Hamiltonian that is dual to a Lagrangian through a Legendre transform, and L sub k are Lindblad operators. In our form, the commutator equal to h times rho minus rho times h is the Lie bracket. The anti-commutator equal to L dagger sub k acting on L sub k acting on rho plus rho times L dagger sub k acting on L sub k is the Jordan bracket, and the dagger is the Hermitian conjugate. The part with the Hamiltonian h corresponds to the reversible part, and the part with Lindblad operators L sub k corresponds to the irreversible part. This form represents the most general Markovian, trace-preserving, completely positive dynamics. So now we take a very concrete, finite-dimensional model to make the generator explicit. Let the collection of all kets ordered at n, where I equals 1, be the bases of agents or wealth classes, and let rho sub t be diagonal in this basis. Then we have the following, where rho sub I of t is the normalized wealth share of agent I, and the bracket notation that indicates Dirac notation. So rho sub t is equal to the discrete sum over all I of our wealth distribution at I of t with the ket of I and the bra of I. We can model wealth moves between agents via Lindblad operators, where k measures the rate that wealth flows from agent I to another unique agent j. Wealth flows positively from agent I to agent j, so k is greater than 0. This means the irreversible part of the Lindbladian is the following. So we have the sum over all I that are not equal to j of L sub ij of rho times L dagger sub ij minus 1/2 the Jordan bracket of L dagger sub ij and L sub ij with rho. Computing this on a diagonal row, we obtain the classical master equation for the normalized wealth share rho sub I of t for an agent I. Remember, k sub ji and k sub ij do not generally commute, so this sum does not go to 0. Wealth flows according to the stochastic matrix k sub ij. This master equation is the discrete form of the Fokker-Planck dynamics we have been discussing. Now we choose the rates through the stochastic matrix. We choose k sub ij so that transitions occurring from the poor to the rich are more likely than the other way around. This corresponds to the failure of trickle-down economics policies under neoliberalism and to what we see under capitalist wealth accumulation dynamics in general. The exact Lindblad generator for such accumulation dynamics in this discrete model is thus the following. On the diagonal, this gives exactly the master equation describing biased accumulation. In the continuum limit of many small wealth classes, this converges to a Fokker-Planck operator with drift and diffusion, and thus we get back the continuous Fokker-Planck equation. Entropy production under this Lindbladian is greater than 0 whenever the process is irreducible and unreversible. This is the exact generator of time moving forward under capitalism, corresponding to an inevitable increase in inequality. Inequality must increase under these dynamics because this dissipative measure induces monotonic growth of entropy and coarse-grained expectation. Let's also consider the category of measurable spaces. Within this category, we can define an endofunctor, where A denotes a measurable space of labor actions and X denotes workers' positions in debt contracts. We can encode a labor extraction in respect to this functor F with a pair X and gamma called an F-coalgebra, where the map gamma performs the following. It maps us from X into the product of A and X. So this maps us from the collection of worker positions and debt contracts to the product of the measurable space of labor actions and positions or contracts. For a state X that's an element of capital X, this map acting on a state says the following. Gamma of X equals the pair A and X prime. This says that a current state X yields an action A with the next state X prime. Since capital X denotes workers' positions in debt contracts, then an infinite unfolding from A0, A1, A2, so on and so forth represents an infinite stream of labor extraction. The semantics of coalgebras treat such unfoldings as inherently non-terminating processes, and since capitalism relies on non-terminating morphisms, this infinite unfolding is central to capitalist exploitation. It is from this notion of endless extraction that we see another contradiction arise, infinite extraction of labor from a system of finite resources, corresponding to the need for capitalism to expand boundaries towards global exploitation. In the coalgebra, the canonical object of infinite streams, denoted A omega, is often a final coalgebra for the endofunctor F of X. Coalgebra morphisms that encode this unique unfolding of processes into infinite streams can be modeled by the following, where zeta maps us from A omega into the product of A and A omega, and that is the coalgebra structure on A omega. Capitalist accumulation is precisely this non-terminating coalgebraic morphism. Because of this, capitalist extraction necessarily wears down laborers and materials needed for resources. The deeper into the unfolding laborers find themselves in this system of extraction, the more the laborer experiences the fallout of becoming a smaller component of an inflating structure of commodification. This is the cog in a machine experience that many workers within capitalism can relate to, as the laborer loses connection with themselves, as their identity relations become constrained to their ability to contribute to the higher profit margins of a company or market that dominates them. Worker alienation then corresponds to the following projection map. A omega into A. This projection map considers only the current profit extraction and ignores everything else. And that occurs through a forgetful functor. Workers see only the local immediate extraction event, and the system, management, and capitalist, if you will, sees the full infinite unfolding. The co-algebra thus shows structural myopia for the individual state. Every local system is subsumed by the global extraction process, and there is no alternative endpoint within the co-algebraic semantics. This corresponds to the feeling of, well, there's nothing I can do about this but embrace what I can't control, and as such, identity itself becomes secondary to the system's projection onto commodity output. Thanks for watching.